In this video, we're going to look at what we understand by the term metallic bonding and how metals form giant metallic lattices. So the first thing we need to do is make sure we understand the term metallic bonding. So the metallic bond is the attraction between the positive ions, the positive metal ions we could even say, and the delocalized electrons. So we're just going to write that key term in. So the metallic bond is the attraction, so it's this force between positive ions, and in this case we could put metal ions in front of that, so positive metal ions and delocalized electrons. So what we need to remember from GCSE is that in metals, these positive ions pack themselves together. So try to think back to that year 7 diagram you drew of a solid, particles all lined up in rows, so they pack together in layers, so in these rows in a regular pattern, and this then repeats behind in further layers. So we're going layer upon layer upon layer in a 3-dimensional arrangement. And because there is just lots and lots and lots of these ions, we say that this is called a giant, and it's a metallic, because we're going to have different types of giant lattice, and this one is made of metal, so we call it a giant metallic lattice. So the metal ions are surrounded by these free-moving electrons. So these electrons that can go wherever they like, they're not fixed to one location, and so we call them delocalized, not localized. So not fixed, not tied. So not fixed to a particular atom. So they don't need to stay where they currently are, they're free to move. And what do we mean by giant? Well, we mean that this thing goes on and on and on. We would say it was endlessly repeating. We can't count how many metal ions are in this giant lattice. It's endlessly repeating. When it comes to adding up the AR of a metal, what we do is we take the formula mass, so the unit formula, and since sodium is endlessly repeating sodium ions in a giant metallic lattice, we just say it's an Na, that's the formula unit, so we just add up sodium from the periodic table. How many delocalized electrons there are will depend on how many electrons are lost from each metal ion. So in an exam, if you get asked to draw metallic bonding in sodium, you need to locate sodium in the periodic table, find that it's in group 1, realise that it loses one outer shell electron into the sea of delocalized electrons, and draw a diagram that relates to that. So we need to draw maybe 9 or so positive ions of sodium, and then the equivalent number of electrons, because they each lose one. So if we're going to draw in a regular pattern, 1, so at least 9, I'm going to draw them in a sort of close packing regular pattern, so at least 9. Sodium's in group 1, so it forms 1 plus ion, so I'm going to put a 1 plus charge in the centre of each of these positive ions, and each one of these loses an electron. Now the electrons are free to move, so they don't line up. I'm just going to put E minus for my electrons. I'm going to put them all over the place, but again, roughly equal numbers. Of electrons. So we're going to label, because it says to label our diagram. So these are our positive Na plus ions, and these are our delocalized electrons. Then it asks us, how would that diagram differ if we use magnesium instead of sodium? So we need to go to the periodic table and locate magnesium. We find magnesium in group 2, which means it loses 2 outer shell electrons to become a 2 plus ion. So when we draw our 9 circles, we don't really need to change the diagram for that part. But we do need to call them 2 plus ions, because magnesium forms 2 plus ions. And then you need to think, well, for every one of these ions, we lost 2 electrons. So we kind of need to double up on our free moving electrons and try to think about how many we're going to need in here. So twice as many. It doesn't have to be perfect, but it needs to look like there are more than there are positive ions because they're losing 2 electrons from the outer shell. They don't need to be exactly twice as many because they are free to move, so they could have moved outside of this section that we've drawn. We've only drawn one small portion of one layer, and therefore we haven't got all of it, and the electrons could have moved outside of this area. So this is my Mg2 plus ion and my delocalized electrons. Now this particular model for metallic bonding is going to become very, very useful to us later on when we try to look at the properties. For example, why do metals conduct electricity? It's to do with this structure. Why can I hammer a metal into a new shape without it fracturing and cracking? It's because of this structure. So this structure is going to become very important in part 2 when we look at the properties that things have based on their structure and bonding. So just to remind ourselves the important terms, the structure, so this word, this little phrase describes the structure in metals, giant metallic lattice, and this describes the bonding in metals. So structure and bonding are going to be very important in this topic.